Listen, if I have sent you an email, then please do respond. Okay, there are a couple of people that I need to talk to. If you have not turned in special homework 3, and there are a bunch of you who didn't turn in special homework number 3, I'd kind of like to know what's going on with that. Anybody want to tell me what's going on? Like the people that turned it in, some of you did great, but I'm a little concerned at this point because a bunch of people didn't turn in this homework, and every homework is very representative of the kinds of questions that you'll see on tests. So I'm concerned about people not turning in homework 3. I'll give you another day or so. If you're looking to turn that in late, email me and let me know so I can know to look back for it and download it and grade it. If you turned it in on time, it's graded and you've gotten it uploaded. You should see that in your student feedback, unless there was an issue. If there was an issue, then you've gotten an email from me. Hossein, I think you've gotten an email from me. I'm not seeing Kenneth Earl here this evening, but we'll keep an eye out. I did run a little pop quiz at the end of the class last time, but we're not going to count that because people had already left the room since we were running a tiny bit over time. But I will be taking an attendance quiz. I'll just be checking attendance sometime here during the evening. All right. So hate to bother people with stuff like that because most of you are attending really nicely. I'd sure like to see cameras turned on. That is required for the course, and everybody, agreed to that, who filled out the form to be allowed to be admitted to this class. So I'd appreciate it if you could remember that. All right. Any questions about the test? The test is in person. So
Wait, when is it? I just joined the class. I'm sorry. When is the test again?
who's talking, please? Who's asked?
Hussein. Hussein.
Hussein? Yeah, this has been on the syllabus since the first day of class. That test 1 would be on September 30th. And it's been in the syllabus that it's in person. You got to make your way to your appropriate campus. If you're HCC, Hartford Community College student, a TUNE student, then you're going to be taking it in room 114. If you're a TU main campus student, the test is in York Road 320. It's on the 3rd floor. Just come through the main glass door for the math department, turn left, and York Road 320 will be on the right. It's the conference room. So this has been, this should not be news because it's been on the reading page and on the syllabus since day 1. And it is in person. That's not optional. That was something you agreed to as well when you filled out that form, that online form for taking this synchronous online class. So we're trying to decrease any instances of student academic integrity violations by having in-person tests. Other questions about test 1? All right, so I asked you to please work on Tarski Worksheet number 1, and that appears in the day 7 notes. And I asked you to work on those negations of those statements. So tonight, our goals are to go through Tarski Worksheet number 1 and go through those answers so that everybody knows, what kind of answers give you full credit, what's needed for that. And I'm going to unpin this so y'all don't have to look at my big face, the whole time. So we're going to work on that Tarski worksheet together. So please get your notes out. I'm assuming everybody has done what we hoped you would do. So we are now going to start working through Tarski Worksheet number 1. The cool thing about the Tarski Worksheet the kind of solutions is while there's only one way to correctly negate these statements, there are lots of correct ways to write a justification that the original is true or false. And that makes it kind of nice. All right, so problem number 1A was this problem. It says there exists a Z such that circle Z and black Z. So let's think about that. We're going to write the negation first, and then we'll deal with the truth value, but we're looking at figure 1 because we're looking at Tarski Worksheet 1. So the first thing we're going to do is write the negation, and we're going to bring that not symbol all the way through to get full credit for our negation. We're not going to just leave it on the outside of like an and statement. We know that when we negated there exists, it flips it to what, folks?
And all.
Yeah, it flips it. Yep, exactly. Or for all. So we're going to have for all Z, and then we negate the predicate. We'll do this in 2 steps so that we can just practice with De Morgan's laws and other rules that we have for negating compound statements, right? So when we bring this not through this compound and operated predicate here, what should we write? Anybody? But I know. For some of you, this is so easy, right? Because you've done this. And I know that most of you have done this. So we know it's not circle Z, the and flips to an or, and then not black Z. All right, let's get to the discussion about whether or not this statement is true. We're always going to be asked to discover the truth value of the original. So let's look at our figure here. Remember, in this figure, B, D, and G are the gray objects. A, C, H, I, and K are white. And of course, it's easy to see that E, F, and J are the black objects. So we're asking, does there exist an object Z that is a circle and is black? Is that true or false? That there does exist an object Z that is a circle and is black? Anybody?
True. Yes.
Yeah. Yeah. And what object is that makes that statement true? What is Z?
J.
Yeah. So let's just be sure and get full credit by writing that. The original is true. We're always addressing the truth value of the original, even though we may use the negation to help us figure that out. Here, it's super easy. It's an existence statement. We're going to just say, hey, let's let Z equal J. And we just want to verify that the object Z equals J satisfies that it's black and that it's a circle. There are about 100 different ways to say that, but I'll just say something simple. Circle J is black. And that, addresses both components of this compound and operated predicate, right? It's a circle and it's black. Or you could say black J is a circle. Or you could say J is a circle and it's black, right? There are lots of ways to do that. The point is to go ahead and deal with the whole thing. Questions? All right. So now let's work on problem B. B says there exists an object little t such that, well, we need nested parentheses because we've got an or and an and, such that triangle T or circle T, quantity, and gray T. So when we get ready to negate that, we're going to have to kind of watch ourselves because we've got an and an or, and we're going to have to figure out what to deal with first, okay? So in the negation, We know the exists T flips to a for all T. But now we have to negate this compound predicate. So I'll just write it down here because we're going to do this in steps. All right. Now, do you know which of these two operators, the AND operator and the OR operator, we're going to deal with first? When we distribute this not through this big expression, which operator is the operator that we're going to have to cope with first?
The or.
Well, that's the correct wrong answer. Okay, so I was kind of hoping somebody would say that so that we could discuss this. So let's take a look. Triangle T and circle T are grouped together inside this parentheses, right? And that makes one component on one side of this AND operator. Do you see that? And the other component on the other side of this AND operator is gray T. So the two components that we have to deal with first are this compound component and then just this atomic component on either side of the AND. So we're going to distribute the not across the AND first. Let's take a look at what that looks like. This is for all T. All right, so we know that we will negate this entire component. So it's not the quantity triangle T or circle T. So we're going to have to negate that in a minute. This and flips to an or, and then gray T becomes not gray T. So we have just used De Morgan's law, but we've used it applied to the and operator first, because the and operator is the last operator that gets executed if we actually think about this statement. The or happens first because it's inside parentheses. Triangle T or circle T is in parentheses, so that's grouped together. So since this was executed first, when we think about how this is constructed, we actually deal with it last. We first distribute the not across this and operator, okay? But now that we've done that, we can go ahead and finish and completely distribute the not, and now the not gets distributed across the or statement. And that gives us, well, we're going to use still parentheses because this will become not triangle T and not circle T. And that whole thing is being OR'd with not gray T. So we still need parentheses because we still haven't, we have an and an or. Here, there would be no way we could drop the parentheses because we needed to know the not applied to both of the components inside the or part of this statement. Component right here. Questions? So we just have to be kind of methodical about the way that we attack these. So now we're going to ask ourselves, is the original true or false? So here's our diagram. We're asking, does there exist an object T that has two properties? It's gray, that's the one property, and it's a triangle or a circle. So you can look in here. It's kind of easier first just to figure out which objects are gray. Which objects T satisfy gray T? Because whatever T we pick's got to satisfy both of these. So it's sure going to have to satisfy gray T. Well, obviously it's those squares that are in the shaded gray, right? We only have three gray objects, B, D, and G. Remember, the letters that are the names of the objects are near the front of the alphabet, whereas letters that are near the end of the alphabet are our variable letters like T and X, W and Z, Y. Those letters are being used as variable names, but A, B, C, D, E, all the way up to K are object names, okay? And those are the identifying key attribute of the objects, okay? So only B, D, and G are gray. So those are the only objects T that have a hope of satisfying this predicate. But do B, D, or G satisfy triangle T or circle T? Nope, they sure don't. In fact, they're all squares. So in fact, the original is false. Now, there are a lot of different ways to try to explain that. But the first thing to do before you try to explain why it's false is to understand why that statement right up here in blue is false. Does everybody understand why this statement is false? So take a minute and see if you can correctly write, or at least write, a reason why the original is false. And then we'll listen to some folks' reasons and we'll critique those. And as soon as you're ready, if anybody wants to read your reasoning for why the original is false, please do so.
The original is false since there is no such circle or triangle that is gray. And yeah, I think
That sounds good. The original is false. There is no circle or triangle that is gray. That sounds great to me. There are other ways to justify the claim that the original is false, but we'll call this one solution one. The nice thing about this is there's not just one right way to do it, but that sure sounds good to me. Anybody got a different way?
I said there's no object T that is gray and is either a triangle or circle.
That works. I'm going to write that down. I like it. And just be sure and say the original is false, okay? So the original is false. I'm just going to give you that much information. All right, now can you read it again so I can write what you said? Sounded good.
There is no object T that is gray and is either a triangle or circle.
There is no object T that is gray and is either a triangle or circle. I like it. Anybody have a different way to say it? What do you think about this way? The original is false. Because all the gray objects are squares. Which we could glean means they're not triangles or circles. Any of these would work fine for full credit. The point is we're stating very clearly that the original is false. I almost want to put that in caps because that's an important part. But nobody will get any credit if you just write true or false. You know, everyone wants full credit, and the way you get full credit is by some kind of decent justification. Questions? All right, let's move on to 1C. Statement C actually invokes a particular object, the object D. So it says, for all x, square x, or right of xd. So when you see a boldface print letter, that is a specific object D. So this statement has a variable x, but it also references this particular object D. All right, let's go ahead and generate the negation because that step is fairly straightforward. I'm hoping everybody gets full credit on the negation on the test because we have our nice rules that help guide us on how to write a negation. So we just kind of execute it naively. There exists an x such that it's not true that square x or right of xd. By the way, you might be wondering to yourself right now, gosh, Dr. Good, do I really need to do it in 2 steps? No, you don't have to do any of these in 2 steps. You can go directly to the final negation if you're capable of doing that, you know, without any intermediate steps. I'm doing this to help folks that may not feel quite as fluent with De Morgan's laws, but of course now we'll distribute the not across the predicate and we get not square x. And how do we negate right of xd? What's the negation of right of xd? Anybody? This is sort of a trick question. Can I put left of xd?
Maybe.
Maybe if you don't want to get it right, you can. Remember, let's look at like objects A and C. Is A to the left of C? Nope. Is A to the right of C? Nope. So the negation of right of isn't left of, remember? And the negation of left of isn't right of because they could be in the same column. It's kind of like the negation of greater than isn't less than. It's less than or equal to. So remember, when it's a prepositional component, if it's, you know, something about relative position, we just put the negation in front of that relative position predicate, okay? We just keep it not right of xd. All right. Because not right of xd means x is to the right of d, or x could actually be to the left of d, but we don't know that. It could be in the same column. Not right of means same column as or left of, so we just say not right of. All right, true or false, folks. We're looking at the original. So it's a for all. So it says for each object x, x is a square or x is to the right of object D. True or false?
True.
It is true. Can you explain to me why? For every x, either the x is a square or the x is to the right of D?
For all x, there is an object that is to the right of D or is a square.
Well, you threw in a there exists. You said for all x, there is an object, and there is no existence. This isn't multiply quantified, okay? So that's the first thing. This is just singly quantified. All right. But let's just remember what we have to do to justify a for all statement, folks. To justify a for all statement, for all X, we have to think about each of these objects X one at a time, and we have to make sure that the predicate holds for each of these objects. So for example, when X is A, either square A has to be true or right of AD has to be true. Is either one of those true for X equals A? Well, let me ask you this. Is square A true? No.
No.
Yeah, that's not true. Okay, good. Now, right of AD. Remember, the first variable or letter goes out front. So right of AD is the statement that A is to the right of D. Is A to the right of D?
Yes.
Yes, it is. It doesn't have to be in the same row to be right of. It's in a column that's to the right of the column in which D resides. So it works for A because it's to the right of D. B, both components of this predicate are true, right? B is a square, so square B is true, and B is to the right of D, right? Right of BD is true. In fact, what about C? Well, it's not a square, but C is to the right of D. You start to see what's going on here. All these objects that are in these columns that aren't the leftmost column, all of these objects X will satisfy right of XD. That only leaves two other objects that we have to deal with kind of separately. What objects X do not satisfy right of XD?
F.
F sure does not satisfy right of FD because F is not to the right of D. Any other objects fail to satisfy right of XD? What about when X equals D itself? See, this has to be true for all X, including X equals D. Just because D is mentioned later in the predicate doesn't mean that we get to discount it. When we are looking at all X, we've got to also examine X equals D. So you see what I'm saying? But it's going to be okay because D is a square. So square D is going to work out the same way square F works out. So when it's a for all statement, okay, and we're trying to justify that it's true directly, not by looking at the negation, but by just directly trying to understand why it's true for all X. It can be smart to group the objects into groups where one of the groups satisfies one component in the predicate if it's an or operated predicate, and maybe the objects in the other group satisfy the other component of the or operated predicate. Remember, this is an or operator. So an object X will satisfy this statement if it's a square or if X is to the right of D. And every X in this figure is going to satisfy that one way or the other. So let me just show you that there are, a couple of ways to slice this to kind of not have to one by one individually mention every single object X. We don't want to do that if we can avoid it. And we don't have to because we can be a little smarter than that. The original is true, okay? Now, if X is D or F, so if X equals D or X equals F, then square X is true. So the predicate holds. Remember, the predicate is the whole condition. In this case, it's an or operated condition. This whole thing is the predicate. This whole condition, square X or right of XD. So if X is D or X is F, square X is true, so this or operated predicate holds. Well, the other case would be that X is some other object besides D or F. So you could just write if X is any other object, then X is to the right of object D. So those X also satisfy the predicate. So it's true for all X, because we've kind of smartly, separated the all X into two groups, the X's that are to the right of object D, and then the two X's that aren't to the right of object D, but they're squares. Questions? So, I mean, understanding what this statement says is going to make it easier for you to do a reasonable analysis. Like being able to read this statement and understand what it says. It says for every object X, X has to be a square or X has to be to the right of object D. Like getting what that means, sort of like intuiting what that really means, should help you write your justification. Questions? All right. Let's move on to the next one. The next is an if-then statement. The next statement is for all Y, white Y implies below YA, where A is the specific object in the Tarski world because it's a letter near the beginning of the alphabet and it's in bold print rather than italics. It's hard for me to write bold print, but it is on the paper and it will be on the test. So let's just write the negation. So here is good review for test 1. We're negating an if P, then Q in a minute here, right? Because we're going to have to bring the negation through this predicate. So the for all changes to there exists, of course, and then we negate white Y implies below YA. So we want to take one more step and bring this not completely through this predicate. So what is the negation of if P then Q, folks? This is super important. We'll do it over here on the side. The negation of if P then Q. What is it?
P and not Q.
Exactly, nice. P and not Q, because if it's not true that P implied Q, then P happened and Q failed to follow, right? So we just apply that rule, understanding that P is the statement white Y and Q is the statement below YA. So we get white Y, just keep your P exactly as it is. If it had a negation on it, you would keep that, but it doesn't. And not below YA. Now, there are several ways to try to analyze this. We can look at the original statement and try to figure out what it means and see if it's true. Or we can realize the statement and its negation always have opposite truth values. It might be easier to see if the negation is true because it's an existent statement. I think it's about 50-50 on this particular example. Here, let's look at our figure. And let's see if we can understand. This original says, hey, look at each object Y. If the object is white, it needs to be below object A. If Y is white, then Y should be below A. Is that true? Any ideas? I see a couple of people sort of maybe tentatively nodding your head, right? Let's take a look at the gallery. What do y'all think? So we look at each object, right? It's got to be true for all. And I know you've got your papers in front of you. At least I hope you do. Maybe I'll pin it again. Anybody? Another way to kind of try to figure it out is to look at the negation, because sometimes existence statements are easier. The negation says there exists an object Y that is a white object and it's not below A. Not below YA means Y is not below object A. Does there exist a Y that is white and is not below object A?
Yes.
Oh, thank
Yeah.
you. What Y is white and is not below object A?
Object A.
Yes, object A is white, okay? The only gray objects are B, D, and G. So A itself is white. It satisfies the hypothesis of this if-then. So the conclusion below AA would need to follow. But A isn't below itself, okay? It's on the same row. It's in the same row, right? So the original is false. The negation is true. And so if you want, that might be the easiest way to explain it. The original is false because the negation is true. It's always, I think, easier to deal with an existentially quantified statement as far as justifying it. Let Y equal A. Then white A holds, right? And not below AA holds. So I'm actually justifying that the negation is true in order to back up my claim that the original is false. Remember, a statement and its negation always have opposite truth values. So if it's easier to deal with the negation, right, then you can do that. Just be sure that you write the correct truth value of the original, whatever it happens to turn out to be. All right, so that's problem one using this figure one. And now we're going to move on to problem two, unless there are any questions on part D of problem one. This problem we just did. Does anybody have any questions on that? I don't see any hands. Everybody good? All right, so this is the game. This is the Tarski game. All right. All right, let's start with problem two now. So we're going to use Tarski figure two. And of course, I just wanted you to see that not every Tarski world has to look the same. So for E, here's the statement. It's a double quantified. there exists an X and there exists a Y. So now we're up in the ante. We're getting multiple quantifiers now. There exists an X and there exists a Y such that same color XY and not same shape XY. So it's a double exists. We have to find an X that exists and a Y that exists, that they are the same color but not the same shape. When you start looking at figure 2, I think you'll be able to see pretty quickly, you know, how that's going to pan out. But before we get to the truth value, let's go ahead and deal with the negation. Same rules apply with the negation as with a singly of a multiply quantified statement as with a singly quantified statement. Both of these, there exists, flip to for alls. And it makes sense. If it's not true that there exists an X and there exists a Y that satisfies this predicate, then for all X and for all Y, the predicate fails. I'm leaving the not outside the predicate for the moment, just to emphasize that the negation of a there exists. It makes sense for it to be a for all for all. All right, now we're going to go ahead and finish the negation by bringing this not through this and operated compound predicate. Okay, so when we bring the not through, of course, same color XY becomes not same color. No big surprise there. XY. The and flips to an or. What happens to not same shape XY when we distribute the not across that?
It becomes same shape XY.
That's right. Not who's there? The original. Not P is just plain old P. All right. So here's the negation that for all X and for all Y, not same color XY or same shape XY. So yuck, it's a for all. I don't want to deal with that if I can avoid it. I'd rather go right back to this there exists statement, right? So what do you think? Do there exist an X and a Y that are the same color and not the same shape? And if
Yeah.
so, yeah, sure. There's about a dozen different X's and Y's you could pick, okay? So here's the thing to understand is you only need one example to show the original is true. All right, so just understand that there might be, like, we could pick A and C, right? They're both white and they're not the same shape, or we could pick D and E, or J and E, or I and K. See what I mean? Like, you don't want to go through all those. You don't have time. You don't need them. You just need one X and one Y that make the predicate true. So pick your favorite, you know, pick your pleasure. Pick your X and pick your Y. All you need is one of each. Just I'll put this note, lots of possible choices for X and Y, but we don't want to pick a lot of choices. We want to just pick one. So here's just an example choice. You got to pick one. You tell me what should I pick for X and what should I pick for Y? Anybody?
E and K.
Okay, let's let X equal E and Y equal K. All right, so we've identified X, we've identified Y. So we've shown they exist. Now we just want to verify that they are the same color and they're not the same shape. So we can just state, hey, they're both white. That verifies same color and shows understanding. It's very specific. And E is a triangle while K is a circle. Or but K is a circle. Right? You just want to kind of write it in ordinary English in a way that indicates, hey, I get this. You know, I understand what's going on with this. Questions? All right, let's keep going. Problem F. It's kind of simple. It says for all X below XA. In fact, I'm suppressing the extra set of parentheses. I kind of went buck wild when I typed this up. We don't actually need parentheses around this predicate below XA because it's not a compound predicate, right? I was sort of in parentheses mode or something, you know. So we don't need those parentheses. You can just write below XA. If you do write the parentheses, it's not wrong. Okay, so negation. Super simple negation. Can do this all in one fell swoop. There exists an X such that not below XA, obviously. There is an object X that is not below object A. This is the specific object A. So, true or false? Talking about the original. For all X, is X below A? Or, you know, if you want to talk about the negation, you know, you can translate what you understand about it to a truth value for the original. What is the truth value? Go ahead.
Oh, the original is false.
Why is the original false?
The original is false because object A is not below object A.
Yeah, we're back to this whole thing about A being in the top row. Exactly. So the original is false. We're actually justifying the negation. You know, when X equals A, not below AA is true, which makes the negation true. And if the negation is true, that means the original is false because they have opposite truth values. All right. Let's look at G. G is the statement, it's doubly quantified. And I went buck wild with parentheses. I didn't really need this outer parentheses. You could write it, there exists an X such that for all Z, X equals Z or above XZ. Now, these are both variables. Neither one of these is a specific object. We're trying to figure out the specific object X and that would work for all Z. So let's just review a there exists for all statement. It means there is one object X. There might be several that would work, but we got to pick one object X that works for all objects Z to make this predicate true. And the predicate is an or operated predicate, either X is Z or X is above Z. Let's write the negation. Let's just go ahead and power through the negation here. For all X, there exists a Z. Oops, I said for all and wrote there exists. That happens sometimes. For all X, or for each X, there exists a Z such that it's not true that x equals z or above xc. And now we're going to bring that negation completely through that or statement to complete the negation properly. For all x, there exists a z such that, and we do need parentheses. Okay, now let me ask you this. We're getting ready to bring a not and apply it to x equals z. So what happens? How do we negate x equals z?
X is not equal to Z.
That's exactly right. Either x is equal to z or it's not. So if it's not true that x is equal to z, that means x is not equal to z. Now, folks, I just want to remind you what x equals z means. X equals z means x and z are the same object with the same name. Like A is equal to A because A is the same object as A. Okay, look, D and I, they're both white squares, but D is not equal to I. They don't have the same name, okay? Just because they're both white squares doesn't make them equal. Objects are only equal if they share the same key attribute, which is their letter name. Questions? Okay, so X is not equal to Z means these two objects have to have different letter names and, of course, because we're distributing the not across the or, not above XC. That's the correct negation. So now we want to again understand what it means to say there exists an X for all Z. And you've worked WebAssign 3.3 by now, right? So you've had some practice with this. It was designed to give you some practice with this. So does there exist a single object X that works for every single object Z to make this particular predicate true? Is this statement true or false? The original.
False.
Okay, I got somebody guessing false. Explain to me why you think that for all X, there is a correspond, excuse me, for, oops, this should be a Z. That should be a Z. Nobody caught that. If this original is false, that means the negation is true. So you're saying for each X, there is some corresponding Z that is different from X and is not above. And such that X is not above Z. So for each X, there is a Z that satisfies X and Z are different and X is not above Z. Have you checked that for each X?
Yes, for when like X is J or X is K, that satisfies the negation.
That's true, but it has to be true for every X that you can find a Z that exists. You have satisfied there exists an X and there exists a Z such that X is not equal to Z and not above XZ. That is right. But that's just showing exists an X, exists a Z. For the negation to be true, and I'm so glad we're having this discussion because this is really important. For every X, for each X, you have to find a Z that is not the same as X and such that X is not above Z. And you do that for every X, like you did it for X equals J, and you could do it for X equals K. You know, you could let Z be the other one. That would work. You could do it for lots of these, but could you do it for every single object X that you could find such a Z? What X might be a problem with this game?
H.
If X is H, wouldn't Z equals E work? Because H is not above Z equals E. Got some chat, we got some chat going on. Anybody?
Wouldn't it be A, because there's no way to have anything above it?
Hey, what about A? So if X is A, can we find a Z that's different from A such that A is not above Z? You're right. We could never get this part of this and operated predicate to be true for X equals A, because A is above everything except A. So let's go back to the original. It says there is some object X that for every object Z, either X is Z or X is above Z. Well, we're back to this situation where when we start thinking about all objects Z, we got to kind of group them together in a smart way. If we look at X equals A, if we let X be the A be the X that exists, then for every Z, can't we show that this is true? Well, either Z is A, in which case X equals Z is true because A equals A is true, or Z is not A, and above AZ will be true, because for Z equals B, C, D, E, all the way to K, above AZ works. For Z equals A, X equals Z works if we choose X equals A. So the original is actually true. Let's see if we can write this up. Let X equal A. For object Z, we got to look at all of them, okay? Well, if Z equals A, then, A equals A holds. For Z not equal to A, above AZ holds. So the predicate X equals Z or above XZ holds for all objects Z when we choose X equals A. So this is a tricky one. It's kind of a mind bender, and you may want to come back, think about it, and think about maybe your own way of writing a justification that it's always true. When we have a picture like this with an object all the way at the top by itself, this is going to work out. All right, let's go to number 2H. That statement says, for all X, there exists a Y such that same shape XY and same color XY. So listen, this is quite different from there exists for all. Okay, for all there exists means for each X, we have to find a partner Y that exists to make the predicate true. And you had some WebAssign, and we discussed this, before when we first started talking about multiply quantified statements on day 7. This is a discussion. What's the difference between there exists for all and for all there exists. So when it's for all there exists, we're going to think about each object X one at a time, and we're going to try to find the Y that corresponds to X. Like different X's can have like their own partner Y that makes the predicate true. That's not the way it is if it's there exists an X for all Y. If it's there exists for all, we have to find one object X that works for all Z. But here, we don't have to do that. We don't have to find one Y that works for all X. For each X, we can hunt for its own kind of private partner Y. Now, there might be a Y that works for all X, but there doesn't have to be. It just means for each X, we've got to find a Y. All right, let's write the negation. Let's go through that. So we know it's going to flip there for all to there exists an X, and there exists a Y to for all Y. And then we're going to negate, of course, this and statement. And that's super simple to do. I know everybody in this room can use De Morgan's law to distribute the not through this and operated statement. Okay. So let's go ahead and do that. So there's the negation says there exists an X such that for every Y, X and Y are not the same shape, or X and Y are not the same color. All right. Like I said, I'm expecting people to get full credit on the negations. Here's our picture. But do we even need a picture to figure out whether the original is true on this one? It's kind of a trick question. Now, I know you all wrote the negations of all of these in preparation for class, but you may not have really thought about the difference between H and the next statement I. And that's kind of a big clue. The only difference between statement H and statement I is that statement I has this additional component in the compound predicate. That should have been a clue.
H is true.
H is true. For every object X, we can find an object Y that is the same shape and the same color, even when that object X is X equals F. Why is it true?
X can equal F and Y can equal F.
That's right. Nobody said that Y had to be different from F. So this is the deal, folks, in mathematics. Don't make your life harder than it already is by imposing restrictions or constraints on a problem that are not there. Nothing in the statement H required that Y be different from X. So that's the thing to notice. The predicate of the original statement does not require that Y be different from X. And in fact, we pick Y equal X to make this true. So the original is true. how do we talk about it? How do we justify it? Well, we're looking at each X. So we just say, hey, for each object X, choose Y equal X. Then both same shape XX and same color XX are true. And by substituting in the X for the Y, it really drives the point home here in this little discussion. So for I, of course, it's the one that, you know, where it's not going to be true because we have a more interesting compound predicate. I says for all X, there exists a Y such that same shape XY and same color XY and X is not equal to Y. So that precludes us choosing Y equal X because this is an and operated predicate. All these components have to hold in order for the statement to work, and it's got to be working for every X. We have to find a Y that is the same shape and the same color. And we can't do that for X equals F, can we? There is no other object Y different from X equals F that is a black square. Let's go ahead and write the negation just to be complete. There exists an X such that for all Y, we can do this in one fell swoop, not same shape. I'm going ahead, I'm distributing this not through the predicate and switches to or, not same color, of course, XY. This and switches to or, and the negation of X is not equal to Y, of course, is that X is equal to Y. And it's kind of gnarly to try to talk about the original being true because the negation, excuse me, the original being false because the negation is true, but you can, I mean, in some sense, we kind of are. We're coming up with an X that exists, namely X equals F, that no matter what Y, if you look at every single Y, either Y won't be the same shape or it won't be the same color, or it would actually be Y equals F. It's very awkward. You can just be more intuitive and you can just kind of show that you understand what's going on by being more intuitive in your response. The original is false. Let X equal F. It is the only black square. And that shows a lot of understanding of what that predicate, same shape XY and same color XY and X not equal to Y means. You know, the black is the same color, square, same shape. The word only is really encoding this idea that X cannot equal Y. Questions? So you endured, you know, what could be quite, you know, considered tedious, but it's important practice with understanding multiply quantified statements. And in fact, it should help you on the test. Your special homework it's a fairly quick turnaround. You know, our special homeworks are due on like, you know, Wednesdays and I don't know, Sundays or something, but I'd like you to get it to me Wednesday so I can go ahead and grade it and get it back to you before the test Monday. And that special homework is already posted. It is to, at least on the reading page, it is to work worksheet 3, which you have. It's in day 7 notes. Okay, and it's, A, B, you can call it problem 1, but there are this many parts, and it's part 1, right? The negation, by the way, this should say a tilde here. You can see how old this worksheet is. Back years and years ago, F used the different symbol for the not, and she changed it to the tilde. So you can tell how old this worksheet is. And then 2 and 3, determine which is true, the original or the negation, and then justify your response. If you want, you can just, state the truth value of the original. If you want to do that and then justify it. You can just do this as part 2, the way we did worksheet 1, or you can do it in 2 steps like this, just be consistent. So listen, for each one of these, go ahead and work all 3 parts before you move on to B. So, for statement A, go ahead and go through all of the parts, then move on to statement B. Okay, because I need to see it all in one chunk, right? I don't need to be like looking at your negations and then 3 or 4 pages later, looking at whether or not, the original is true or false. Okay. So just, keep it together, do it the way that we did it here, where for each statement, you go ahead and go through all the steps to make a clear argument about whether the original is true or whether it's false, please. So you can go ahead and start working on it, because all I'm going to do is refer you to the day 7 notes, Tarski Worksheet 3, to ask you to work that. So. And that'll be due on Wednesday. So Wednesday, we're going to do a short review for test 1. Okay, we'll spend maybe 15 minutes just bullet pointing the main things that you need to know. Listen, folks, important announcement. Is everybody still here? Let's go to the gallery view. I want to take attendance. Did we lose anybody? All right, let me take attendance. You have to bring your TUID to the test on Monday, okay? Half of you, I only see the top of your head or whatever. Like some of you, I see you really well. And some of you come to office hours. But you need to bring your TUID. If you are a TUNE student, then you need to bring your ID for sure, because there's going to be a proctor there and they can't give you the test if you don't have an ID. It needs to be a picture ID. You should have a TUID. So be sure and have a picture ID for your test. So who do we got here? We got Nick, Kendall, Needy, Danny. Nice job on your homework, by the way. I hope you don't mind my saying so. Eric, you too. Marcus. Okay, and Zane is here. Edwin. Nice job. Matt Smith, Ronnie, Stephen, Hossein. I need to talk to you after class, so stick around. Brianna, Gabriel, and Ahmed. So listen, if you haven't turned in homework 3, I'm giving you a reprieve. I'm going to give you another day to get homework 3 in. Go ahead and upload it. It'd be nice if you'd email me and let me know when you do that. And you might tell me why. I don't know. Was it terrible having a pre-recorded lecture? I mean, was that the deal? Was that what made it so hard? I've never seen so many people not turn in homework. What's going on? Anybody want to talk to me and tell me? Otherwise, you're excused. For those of you who are turning in your homework on time, I appreciate it. But I need to know what's going on. Why a fairly large percentage of people did not turn in their homework number 3. All right, well, you need to talk to me. And kind of a one-time thing that I'm going to let you have another 24 hours. You need to work that homework. Okay. All right, so stick around, Hussein, if you've got a minute, please. Anybody else who wants to visit has some things to discuss, stick around. And we can talk. I can put people in the waiting room. I'll stop the recording so that we can have a private discussion. I'll stop the recording.